Okay, here is part two, as promised, binomial distribution, getting more into the mean and variance. The variance, we'll see, has a relationship directly to the so-called standard deviation. So in your formula booklet, you'll see notation referencing the binomial distribution. The random variable x is binomially distributed, where here is n and here is p, the likelihood of success. And there are two formulae here, and one of the purposes of this podcast is to bring these formulae alive, as well as to pursue something that's kind of a standard GDC-based solution we need. So the mean, or expected value, appears to just be n times p, and the variance, which has some relationship again to the deviation. We'll look more closely at these two concepts when we talk more formally about statistics that's coming up. So a little bit of background. If a coin, a fair coin or unbiased coin, is tossed, let's say 20 times, and the likelihood of the coin showing a head is of course 1/2 because the coin is fair, we would expect that coin to show a head, of course, 10 times, right? As it turns out, the mean, or number of heads, or the expected number of heads, is actually the n of 20 times the likelihood of success, which is 1/2. That's where it comes from. Similarly, if we were to roll the die, let's say 30 times, the likelihood of the die showing a 2, of course, on any one of those rolls is 1 chance out of 6. Well, we would expect that die to show a 2 5 times, which actually is, of course, the 30 times the 1/6. So, 5 out of the 30 accounts for the 1/6 that we would expect for the 2 to show up. That's my way of providing support for the more critical formula from the formula booklet, dealing with the mean or expected value simply being n times p. That's kind of an inductive approach to have you buy into that. The variance, which can sometimes be notated as sigma squared, will, as it turns out, be n times p times q, where of course q is the likelihood of failure relative to success. That's going to be its complement, 1 minus p, and the square root of the variance is simply what the standard deviation is. But much more on this later when we get to the statistics component of the course. A couple of examples. When iPhones are delivered by the factory, it's found that 5% of the phones in a major shipment, right, in each production, are actually defective. So let's say out of that huge number of phones delivered in that one order, let's say a random sample of 80 iPhones is taken. Let's actually find the mean and standard deviation of the number of defective phones in the sample. Well, to go back to that notation, if I'm the random variable x and I'm binomially distributed with this kind of notational breakdown, n, of course, would be the 80 that's in terms of the trials, or the number in the sample. And in this case, if 5% are defective, then the probability of that sort of quote-unquote success of being defective is 0.05. So using this straightforward formula, the expected number, or the mean number, of iPhones that we would expect to be defective, of course, would just be the product of those two, which would be 4. And so further, just to go a step further with the standard deviation, we're just building on this formulaic approach. For now, n times p times 1 minus p, and the root of that ends up being around 1.95. This, for currently, is just kind of a value for us. We will get into this nature of the deviation, which many of us know deals with spread relative to the mean, how clustered or close the data values are to the mean versus how spread out they are. But more on that, again, in the formal statistics part of the course. Okay, a second example that is often asked, a bit more unfamiliar. So let's talk about a bag that contains a large number of colored candies, where we know 25% of those candies are red. So the remaining candies in the bag are non-red. We don't really care about the color. We've got sort of R versus R prime here in terms of the complementary colors to the red that are in there. So children start to pick at random candy from the bag. The question is, can we determine the number of candies that must be picked so that the likelihood that there is at least one red candy among them is greater than 0.95. You'll notice that there's no n value here, and that's because what we're actually trying to find is n. So here's the question just repeated. So let's actually let x be the random variable, the so-called number of red candies. So either you're red or you're non-red, so you're binomial in terms of that random variable. We're interested in n, and we know that the 0.25, the likelihood of success of a red candy is 0.25 as stated. So n is the unknown. So what we're interested in finding, given that we know that the probability that the random variable selected is at least 1, so 1 or more, has to be greater than 0.95. That kind of centralizes what it is we're trying to do here. Well, 1 or more out of some unknown n number is impossible to deal with in terms of kids reaching into a bag and they keep pulling out a candy. But we can be cleverly using the complement of that event. So we also know that the likelihood that x is greater than or equal to 1 is, of course, 1 minus the probability of exactly no red candies at all. So that's the complement to that. So since this is the basis upon which we're trying to build some kind of a structure, and since this left-hand side is essentially 1 minus the complement, this piece here, that in yellow is what we're focusing on and what we can actually work with. Because what is the likelihood of not getting any red candies at all? Well, that just is kids reaching in and getting non-red, 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 and that's happening 0.75 times 0.75 times 0.75, some unknown n number of times. So this guy falls into the system as just 0.75n, and so the basis for the construction, which is this yellow equation going all the way back to what it is we're trying to resolve, is just 1 minus the 0.75 raised to some unknown n has to be greater than that. So that's where we are in terms of proceeding. So a couple of methods in terms of attacking that. The first method that's rather classic is to say, okay, there's an unknown up in an exponent, which not unsurprisingly leads us eventually to a future involving logarithms to resolve bringing that unknown back down. So a little bit of a rework here. So all I've done is bring the negative term over to the right-hand side and subtracted 0.95. So here we are here with something that is looking a little bit more straightforward to work with. And so given this has to be greater than that, we know that we can apply the log of the 0.05, and that has to be greater than the log of the 0.75n. And so log of some base to a power is, of course, n times log of just that base. So that is employing the actual log property that we're aware of. We are interested in solving for n, so we're going to divide both sides by the log of 0.75. A little bit of a side comment here. We need to be careful. What sign, plus or minus sign, does the log of 0.75 have? Well, that's saying 10 raised to what power is 0.75. And on your GDC, you could confirm that the log of 0.75 is actually equal to this negative value here. So when you divide both sides classically of an inequality by a negative, you have to reverse the sense. And that's why this sense gets reversed, and you can see the greater than portion will turn around and be opening to the n side. So if you have a think and look more closely at what's going on here algebraically, and considering the reversing the sense of the inequality, as we say, because we're dividing both sides by a negative, here's where we are. So n's got to be bigger than whatever this is, this being the ratio of these two logs, which in your GDC hands you around 10.4. So you have to be at least up to 10.4 sort of draws or picks from the bag, which means you've got to round up to 11. So that n of 11 is saying that at least 11 candies must be picked from the bag to ensure that the likelihood that there is at least one red candy among them is greater than what we're actually being asked, the 0.95. There is another way. If you don't like the logarithmic way, there's a method that deals with simply saying, okay, we're trying to resolve, if you will, where this value, actually I'll go here, where this sort of left-hand side is greater than this right-hand side. So I have not even done any algebra. So that's going to go into the GDC as y sub 1. That's going to go in as y sub 2. And here we are right here with those representations. And what I've done for you is I've provided a window that took me, 90 seconds or so to track down as the most convenient window. So if you actually explore this yourself and put in these values for your window, because this function deals with pretty tight, small values at times, you should get something that looks like this. You could experiment right now with trying to find, of course, the intersection between those two. And you should be able to confirm doing the left-bound, right-bound thing, given the chance of the GDC to find the value in between, that when you enter on that with that so-called guess feature, it'll hand you the 10.4s that we expect, and of course you round up to 11. That's pretty much it. Rounds out a lot of the basics of the binomial distribution, and hope that helped. Ciao.